Okay, we're going to do this example of a Cauchy Euler nonhomogeneous equation. So similar to one that you're going to be doing in the homework. And I've got the problem written down right here. T squared y double prime minus 4ty prime plus 6y equals t cubed plus 1. So this is non-homogeneous. The first thing we're going to have to do is we're going to solve the homogeneous case, in other words, where this side is 0. So we're going to use the characteristic equation to solve the homogeneous equation. And remember, our form is at squared y double prime plus bt y prime plus c equals 0. And we're going to use the characteristic equation to solve this. And notice we've got the characteristic equation right here. That's ar squared plus b minus a, don't forget that, times r plus c equals 0. And so we've copied down the left side. The a is 1, the b is -4, the c is 6. So let's see if we can apply that. So we would have 1r squared plus -4 minus 1, that's the a, r, plus 6 equals 0. And -4 minus 1 is -5. So we've got this equation right here. And that can be factored, lucky us. So we will factor that. And so we've got r minus 2, r minus 3 equals 0. And that means r equals 2 and 3. Now, since this is a characteristic equation, a Cauchy Euler, and it's not a regular equation with constant coefficients, then our y1 and our y2 are power functions, t squared and t cubed. And so our homogeneous solution would be c1 t squared plus c2 t cubed in either order, but we have to choose an order. All right, so we're going to use these now to solve this equation using variation of parameters. So that's going to be our second step. So I'm going to slide this up. We're going to use our variation of parameters to solve that now that we've found our y1 and y2. So I can slide that up to the top. All right, so let's get started. We've got to find our Wronskian. y1 times y2 prime minus y1 prime y2. Using these right here, so we've got t squared, 3t squared, minus 2t times t cubed. We get 2 to the 4th. So that's our Wronskian. And we're going to use our two formulas. We're going to use our first formula is v1. And v1 is the integral of negative f of t, which is the right side of our differential equation, times what we've chosen as y2, which is t cubed, over a is what we had when we first started variation of parameters. But now notice a is not a constant, it's a function. So whatever's in front of y double prime has to be down here in the denominator. So it's a of t now and not just the number 1. It's the function t squared. And we just found our Wronskian to be t to the 4th. All right, so we're moving right along. This is really nice, right? We can simplify, pull the negative out. We've got t cubed plus 1 over t cubed. All right, let's just divide through by t cubed. We would have the negative of the integral of 1 plus t to the -3. Antiderivative of 1 is t. Antiderivative of t to the -3rd is t to the -2 divided by -2. And so we can pull through that negative. So we've got -t plus 1/2 t to the -2. This is our v1. All right, now in just a minute we're going to calculate v2. And remember, v2 has a positive here and a y1 here. So let me see if I can slide that up a little bit. Here is our v2. F of t y1 over a of t times the Wronskian. So again, I think someone had pointed out, yes, the denominator is going to be exactly the same in the v1 and the v2, so that won't change. But the y1 now is the t squared instead of the t cubed. Again, we can integrate this by simplifying and dividing. So we'll divide that through. We got to be careful not to use the power rule on t to the negative 1. It is the natural log of t. Antiderivative t to the negative 4th. Add 1 to the power, divide by the new power. That's the power rule for integration. Notice I left off the absolute value of t here. And we can do that because when we're solving Cauchy Euler, we're going to assume that t is positive. If t is negative, obviously t can't be 0 because we're dividing through by the t squared to put this in general form. So t can't be 0, and if t were negative, we would solve this in a slightly different way. So we're going to assume that t is positive for these. All right, so I think we've got everything that we need to find our general solution, because all we need is y1 and y2 and v1 and v2. So I'm going to slide this up. All right, so our general solution, y sub g, is v1y1 plus v2y2 plus c1y1 plus c2y2. And we will go ahead and put those in. All right, this is our v1 that we found right here. Whoops. Our y1 was t squared. This is our v2 that we found right here times y2. c1y1 plus c2y2. So these are our two unknowns, our two constants. However, we can simplify this answer quite a bit, and yes, we do want you to do that in your homework problems. So let's multiply this through by t squared. Let's multiply this through by t cubed. Notice here we're going to get a constant, and here we're going to get a constant. All right, so let's do that. We'll multiply those through, and we get negative t cubed plus 1/2 plus t cubed natural log t minus 1/3 plus c1t squared plus c2t cubed. All right, but wait, hey, I think we can even do more with this, right? The 1/2 and the negative 1/3, that's 1/6. Also notice that this right here, negative t cubed, and a c2t cubed can be combined, and this we say this is absorbed by this term right here. There's just two t cubed terms with different constants. So we're going to just leave this one off, basically, since those are exactly the same type of term. And so when we do that, we would have our final answer, y equals 1/6 plus t cubed natural log t plus c1t squared plus c2t cubed. Ta-da!